Good day, good people. Let us look at centroid, chapter 6, the bending of beams. On the bending of beams, we'll be working with this formula here. All right. Now, this formula we'll use it to examine the critical point of the beam. Remember, in chapter 5, we calculated the reactional support, we calculated the bending moment. Then we said it that if this is your beam, simply supported beam, then you are having a force acting on your beam, then it will bend like this. Now, this would be the critical point. Then what do? We cut the critical point into two, then we look at the face of that critical point. What's happening on that beam, on the face of that beam. Right, that's what we said, that we will be using this formula to examine what that critical point of your beam. It is called the critical point. Now, why is it called the critical point? That simply means that that's the possible area where your beam can fail you as a result of what? Of the applied force. Right. Then in chapter 5, we did look into how to calculate the bending moment. We said bending moment equals to force multiplied by distance. That's the formula that we've used. We've actually said it is plus or minus force multiplied by distance. We consider the direction of what? Of the force. But here in the bending of beams in chapter 6, when calculating the bending moment, it will depend what beam are we dealing with. If it's a simply supported beam, meaning you are having a beam supported, then you are having the W acting on that beam, then your beam will bend just like that. Now, in calculating the bending moment of this simply supported beam, it will be Bm equals to W L over 4. Now, if the beam has the UDL, right, this would be F1 divided by 2, F2 divided by 2, W divided by 2, W divided by 2. Right. Now, if the beam has the UDL, now in calculating the bending moment, it will be Bm equals to W L over 8, or it will be uniformly distributed load. It has the extra load on top of the beam. It will be UDL squared divided by 8. Now, we will be using this formula to calculate your bending moment. Then if we are dealing with cantilevers, just a simply supported beam cantilever, then it will be the formula that we will be using in calculating the bending moment of a simply supported beam. It will be Bm if it's a cantilever, W multiplied by L. But if the cantilever has the extra load on top of it, if it has the extra load, then in calculating the Bm, it will be uniformly distributed load, right, multiplied by L squared divided by 2, or it will be W L divided by 2 in calculating the bending moment. Now, this is the formula that we'll be using in calculating what? The bending moment, right? Then in calculating the stress, whether it's a stress max or stress mean, it will be force over area. Now, if we are calculating the stress maximum, please make note that we will always calculate the maximum stress from the smallest area. All right, please make note that we will always calculate maximum stress from the smallest area. Then the minimum stress, it will obviously be from the bigger area. It will be force over area, but it will be the bigger area. It will be the bigger area if we are looking for the minimum stress stress. And then we said we therefore need to know how to determine which stress dominates at the critical point. Remember, you are having the beam, then you are having your weight on top of your beam, then we get to determine the critical point. We said it that the stress at that critical point, stress at this critical point, it is at its maximum, right? But we then have to establish what type of stress is dominating on that critical point or at that critical point. It could be a stress tensile that it is dominating, or it could be a compressive stress, but we then have to determine. Now, when you are having the force applied on your beam, this is what you'd realize. You'd realize that the forces inside that beam, they are causing, or rather the force would be the force compression, because they are converging. Then outside the beam, you'd realize that the beam is being pulled away, or stretched. That means at the bottom, the force that it is dominating, it is what? It is force tensile. Then we will be using the bending stress graph to determine which stress dominates. Remember, if we are looking for stress compression, it will be force compression over area. Which area? The area of the critical point. Or it will be stress tensile equals to force tensile over area. Which area? This area here at the critical point. But in determining what stress it's dominating here, the maximum stress that it is dominating, then we will be using the bending stress graph. The bending stress graph, you will write that critical point. Then after you've written that critical point, you will then determine the centroid of that critical point. Now the centroid of this critical point, we know that from there to there it is y, then from here to there it is what? It is x. Now in calculating the critical point, it will be y divided by 2. Then we get what? The centroid of this beam. Now after we've got the centroid of this beam, then we can then determine which stress dominates on that critical point. Then we draw the stress the bending stress graph, right? Then we are able to tell which stress is dominating. We said it that on the inside, the stress, it is compression. Outside, it is what? It is tensile. That means the upper part of this beam here, it is experiencing what? Compression, right? Then the outer part here, it is experiencing what? Tensile. From this bending stress graph, you are able to then determine which stress dominates the critical point. But you will then have to know how to calculate the centroid of your beam for you to be able to determine the stress that it is dominating on that critical point. Let's say in giving you the example, we are having this beam here, right? Then we do calculate our centroid, and only to find that this is where our centroid is, right? Then in drawing the stress bending graph, but this line, this cross, it has to be exactly straight with this center line there. It has to be straight with the center line, not that which I've drawn here, but because of it's an example, and my tools, right, are showing me flames. Now this is where the centroid is. You can tell that from the center to the bottom, it is the bigger area. Then from here to there, it's a smaller one. It means the stress that it is dominating here, it will be the stress tensile. It will be the stress tensile, because the top part, it is the stress compression. It means that the tensile, it is dominating this beam. You can tell it's dominating what? This beam. The fact that the bottom portion, it is bigger than the top portion, that indicates to you that the stress that it is dominating here, it is stress tensile. All right, then in calculating the centroid, I've already touched on how to calculate the centroid. In the centroid, it is nothing but the center of your beam. right? It is nothing but the center of your beam. For instance, if you are having the rectangle, the center of your beam here, it will be y divided by 2, then you get what? Your centroid. If it's a round bar, then you know that your round bar, it will be diameter divided by 2, then you get your centroid, of which your centroid would be radius, because from the center to the circumference, it is what? It is radius, d divided by 2. But if you are given compounded beam, if you are dealing with compounded beam like this one here, let's look at the T beam. This is compounded beam. Okay, if it is compounded beam, then you will then have to use area moment in calculating the centroid. You then have to partition your beam based on familiar shapes that you can calculate their area and their center. For instance, if it's a T beam, I can denote this one as my area 2 and this one is my area 2. That one is area 1, area 2. I know how to calculate the area of this shape here. I know how do I calculate it? It is length times breadth. Then I get what? The area. Then how do I then calculate the centroid? In calculating the centroid of this top part of the T there, it will be, we know that from there to there it is y, from here to there it is what? It is x. Now your centroid, it is made up of y and x. Now it will be y divided by 2. It will be y divided by 2, and it will be x divided by what? X divided by 2, then you get what? You get your centroid. But the fact that you are having compounded beams there, you will then use the area moment. Area total equals to yt equals to area 1, y1, plus area 2 multiplied by y2, whereby you need to then consider the second area there in calculating what? The centroid. Or it will be area total, x total equals to area 1, x1, plus area 2, x2, because your centroid, it is made up of your y and x, right? Now hence we have to use the area, the area moment. This form, we call it the area moment, or the first moment of inertia, or the first moment of inertia, right? Then you'll have to use this formula in calculating the centroid of this compounded what? Beam, right? That's what we spoke about before, you know, we went for school recession. Now then, in calculating the moment of inertia, we said it that when we calculate the moment of inertia, let's say you are given this beam here, right? This would be the depth of your beam, the depth, that would be your y, then this would be your b. Now in calculating the centroid, it will be I equals to b d cubed divided by 12. Now you always work out, or rather when coming to moment of inertia, you are always working out your beam from the strongest side of your beam. Yeah? And the strongest side of your beam, it is always the shortest side. It is always the shortest side of the beam, right? In this case, if this is where I've taken moment in determining the moment of inertia, you can tell that if this is where I've taken moment where? At x-axis, because you always determine it using what? The x-axis. This is your y, this is your x. Now if I've taken moment at x, I'm determining ixx, and the ixx, it is always the strongest side of your beam. Now if I've taken moment on the yy, if I've taken moment on the y, it means I'm determining the weak side, and the weak side of the beam, it is always the longest side. Now it will be IYY. The IYY, this YY, it indicates where you have taken what moment. If this is where I've taken moment, then it will be, if this is where I've taken moment, I'm opposite to what, to the longest side, then it will be D B quad cube divided by 12. Now since well I've taken when coming to IYY on IXX, the fact that this is where I've taken moment, I'm opposite to what, to B, then it will be B multiplied by D cube divided by 12, and this, it is the strong side, and this, it is the weak side of the beam. Right, now when coming to the moment of inertia, we always work from the strong side, but it will depend with the position of your beam. Okay, it will depend with the position of your beam. If you are given the beam in this way, right, you can tell this is my X, this is my Y, and this is where you have taken moment. Okay, if you have taken moment at IXX, then it will be this is the longest side, this is the shortest side, right? Then it will be D B cubed divided by what, by 12, because this is where you have taken what, moment. Now when coming to the moment of inertia, it will always depend on the position of what, of your beam. Okay, don't if you are given a beam this way and you want to change it and be something else like this and work it out from that. But we do have the instances where we have to do that. But for now, let's stick to the given principle that the strongest side, this is how we calculate it, then the weak side, this is how we calculate it. Then we'll drop more videos on moment of inertia. If not mistaken, we have to continue from moment of inertia, because the other elements we did touch them. We did touch on the bending moments, stress, centroid. The one that we need to emphasize, it is this one, and the theory, the parallel theory. Then we need to cooperate it with the parallel theory. Then I will drop more videos looking at the moment of inertia. Thank you, good people.